Hello everyone, this is Roberto Torre and welcome again to the third lecture of NCC networks for the cooperative communication systems. So in this part we are going to talk about the architecture of the network coded cooperative networks. So let's go through it. We left it in the scenario. So the scenario that we are tackling is we have some video servers on the internet which will have to go through the core network, and we will have some mobile users on the other side that will request the same video. The idea is that these video servers will stream through the base stations and they will arrive at the mobile users. In the beginning by unicast, and we are with our system with multicast. So we have here the cellular on the left with unicast, and then on the right we have cellular and Wi-Fi with a short range. This on the left would be the state-of-the-art scenario where we have the whole stream that is going. We have 3 users and we are sending this video, the 100% of the video, to each of the user separately. In the end, through the base station, as you can see, it's going 3 times the traffic. So the good thing is that it is direct and it is completely reliable because it's unicast. However, it's inefficient because we are sending too many streams, and in the end it will not meet the 5G requirements of energy consumption and through this improvement in throughput, for example, that we are looking. But in the end, as we can see, it's inefficient. We are sending 3 streams for 3 users when we can save the resources. How? With these network-coded cooperative networks. On the right, we can see that we are not sending the whole stream, but we are only sending partial streams. So we have this video server that sends, in this case, would be 33%, more or less, a little bit more, because as we were seeing in the network coding part in the key enablers, we saw that we have to send a little bit more of coded packets to be able to overcome the losses. So these extra coded packets, we call them redundancies or simply coded packets. Okay. So we have to send these partial streams, which would not be a third but a little bit more, and then each user will be in charge of recoding the information that they got and retransmitting it to the rest of the users. How? It's going to be done via Wi-Fi multicast. The pros, again, we have a high throughput and the energy efficiency. We'll see this in the evaluation later. And then also the resilience, because we have the mobile cloud. So if we, for example, lose the connectivity somehow, we can still take the connection from our peers that are in the same cloud, and we can still have the communication. The problem would be the extra latency that this system may add, because as you can see on the left, it goes directly to us, to the UE. However, in this case, it will have some jumps that may increase the complexity and also the latency. And regarding the complexity, because we are including network coding in here, which need the nodes, the user equipments will need to recode the stream, the packets that are received, and this of course will take a little bit of resources. So how this network coded scheme works? We have 2 different phases. We have the cellular phase and the cooperative phase, which are done which can be done either separately or at the same time. That depends on the number of interfaces that our user equipment have. So if we have 2 different antennas in our smartphone, we can have first one antenna. We can have the antenna connected to the LTE base station and then the antenna connected to Wi-Fi. In that case, we can do this at the same time. If not, we will have to do this separately. And this is one of the requirements, for example, to see if there will be throughput increase or not. Because if we are able to have two antennas at the same time, of course, the energy consumption will increase, but also and also the throughput, the maximum throughput. Otherwise, if we cannot do this, then the energy consumption will be reduced, and the throughput will also may be reduced. This is one of the trade-offs that this system has. So in the first part, in the cellular phase, then the base station is going to send in a round-robin phase the packets to each of the users. So the way this works is network coding divides the stream into different packets, and these packets are organized also in blocks, which is normally around, like, it's a multiple by 2, so it could be 32, it could be 64 normally. So we're going to send this in a round-robin fashion to all the users. When this is finished, at the end of this phase, each user should have 1/3 of the packets. The idea is that there will be no losses in this part, because it's still unicast and it's LTE, which it's not prone to errors. However, we will encode first the packet also in the server, so the packets that we receive in the beginning are also coded with network coding. There are different protocols that we can use. Then we have at the end of this phase, as I said, each user will have 1/3 of the packet. Then in the cooperative phase, we will have also a time slotted distribution, where each user will take one time slot to transmit their packets via Wi-Fi multicast or unicast, depending on what are the resources on our system, and what are the capabilities of the mobile devices. So let's suppose we do multicast. So in the first time slot, we will have one user, then in the second user, and so on, until all packets from all users are distributed to all the users. At the end of this phase, of this cooperative phase, all the packets will be distributed to all the users. The most important thing here is that we don't think of the video as the whole chunk of the video, okay, and we divide it by 1/3, 1/3, 1/3. But what we do is we divide it in very, very, very small parts, okay, and then we go 1/3, 1/3, 1/3. Then we go to the first one again, and so on. But when we are done with the generation, so when we are done with these 64 packets, that would be the cellular phase. Then we go, and so let's suppose we have 64 packets, the cellular phase. Each one has around 20 packets, 25 packets, and then we will have the cooperative phase. When everyone has the generation, we go back to the cellular phase. Okay, and these are the two phases that, if we have two interfaces, it can happen at the same time. So I could be receiving from the cellular phase and recoding, while I am also forwarding the packets in the cooperative phase in the Wi-Fi interface. That's one of the big benefits of network-coded cooperative networks. So this is a small example where we have the antenna, and then we have 3 different users. As I said, we are going to spread first the information so these 5 packets in a round-robin fashion. So first to the purple one, then to the blue one, and then finally to the green one. Since we have 5 packets, so 2 more, we start again from the purple one and then the blue one. And then the cellular phase is done. Here we are done. In this example, okay, our generation in network coding, this block is the size of this block is 5. Then we have the cooperative phase, or the mobile cooperative phase. In this phase, again, it's time slotted, so the first user multicast to the 2, then the second user multicast to the first and to the third, and the third user multicast to the first and to the second. And we see that in this example we are losing one packet in the second time slot of the cooperative phase. So what happens is that we will at the end we will have one extra coded packet that we are going to transmit. Depending, of course, this number of extra coded packet will depend on the amount of error rate that the Wi-Fi channel has, because Wi-Fi channel with multicast, it is a little bit lossy. So that is how the architecture is going to be. Let's have a small example now to understand more or less how this would work with real numbers. Okay, so let's suppose we are using this conventional system. First of all, we have the antenna and we have 3 packets to send. Then we have on the right we have the total LTE bandwidth that we are going to use, and the short range total bandwidth that could be, for example, Wi-Fi. In the conventional, we have one mobile, one smartphone that is using 10 megabits per second of capacity, of throughput. So the antenna will just connect to that phone, and the total LTE bandwidth will be 10. If we have 2, the same, and if we have 3, exactly the same, as you can see here. So in the end, we will multiply the LTE bandwidth by 3, by the number of users that we have, because they are completely separate. An important thing that you can see here is that if we do this, as you can see, the packets that arrive are not synchronized. And this was one of the problems I was stating before, that if we are, for example, in a bar, and this bar has 3-4 TVs that are streaming, are receiving a stream, and if these packets are not synchronous, then it may happen that the people from some parts of the bar may see a goal or something that happens in the match they are watching before another one, which is, of course, not desired. In this case, here we don't have any kind of short range bandwidth, of course, so this is 0 megabits per second. Then we have the second approach. In the second approach, we have we cluster the users, and we are going to have an antenna here, and we are going a Wi-Fi antenna, Wi-Fi access point, and we are going to share the information. Okay. So I will first start the animation once, so you can see it. Then I will explain it again and analyze it, and then we will see it again, because this is a little bit fast. So let's see. We distribute the packets, we recode them, and then we are able to decode. As I said, this was a little bit fast, so let's start again from the beginning. How does this work? Okay, so each one of the users has a capacity of 10 megabits per second, exactly the same as before. Okay, and then we have 3 different packets that we want to send. These are the raw packets. So what we are doing is we are not sending 3 packets to each user, but we are only sending 1 packet to each of them. So 1 packet would go to the upper one, 1 packet would go to the mid one, and 1 packet would go to the lower one. But these are not going to be the raw packets. No, what we are going to do is we are going to code them here or in the server. We will code them. So the first packet is going to be a coded packet here and here and here, and this packet we will store. And then what we are going to do is we are going to recode this packet. Okay, if we only have 1 packet, it's maybe useless to do this, but when we start having 2-3 packets stored, then it's when it becomes useful. So we are recording the packet. So the packet that arrives here is not the same packet that is going to be distributed here in the multicast network. So in the end, this user will share its packet with this 2, this user with the other 2, and the user at the bottom with the 2 users above. When the 3 of them have, when one of them has the 3 encoded packets is able to perform this Gaussian elimination that we were talking in the video before, and it will be able to retrieve the raw packets. And this will happen to each of them. The thing is that the time when this will happen, it will occur more or less at the same time. Okay. Maybe there will be one user, the last user that has to transmit the last packet will be able to decode one time slot before, because let's go in this example. For example, as I said, the cooperative phase is time slotted. So right before all packets can be decoded in all nodes, we will have the last node to send the last packet. In this part, the last node will already be able to decode all the packets because it has all, and it has to send only his last packet. So and when it is sent, so after in one time slot, then the rest of the nodes via multicast, the rest of the nodes will be able to decode everything. So in the end, that's going to be the expected difference in synchronicity. So what happens with the bandwidth? Despite having these three users, so 10 megabits per second of capacity, we are only sending at 3.3 megabits per second, because we are sending at 1/3. This means that the antenna could send 3 times faster, increasing, for example, the quality of the video, or it can happen that we can have more users receiving at the same time, so more mobile clouds. The same antenna that was transmitting at 10 megabits per second to each, so it was in total 30 megabits per second. Now it's only 10, so this means that this antenna can handle 3 clouds, and if each cloud has 3 users for the same antenna, we will have 9 users. And then the short range bandwidth which is it's a sum of the upload and the download, and it's 30 megabits per second, because in the end, in this case, they will transmit with 10 megabits per second. So the bandwidth there would be 10 per user device. The concept, the most important thing in here, in the end, is that we are going to be able to offload from this LTE to this short range, and this short range will not affect other similar mobile clouds that we may have. So we can have multiple mini clouds in our huge network, and they will not interact and interfere with each other. Now let's see it again. We send the coded packets, and then these packets are received, and this is the point where the packets are decoded. Good. Let's continue. I think it's exactly like doing so. Good.